Good morning, everybody. Hopefully you guys had a good weekend. Let's start with green check marks. And while you're doing that, if you had any questions from 7.1 from last day, throw those into chat. And yeah, you guys have your English test tomorrow. Kind of snuck up on us, which is pretty exciting. I'm just going to go through a little bit of 7.2 today. And then I'll leave 7.3 for Thursday. Again, on Thursday we have a long block. So Thursday we'll finish off 7.3 and we will start reviewing for the final exam next class. It gives us 2.5 classes to review for the final, which isn't a ton of time, but it should be good. What I'll also do, I'm thinking, we'll see how it works. I was gonna pre-record 7.3 for you guys to watch before next class. That way we can spend all of next class reviewing. Anybody be interested in watching 7.3 before the class, or do you just want to show up and just do things like we normally do? Any opinions? Does anyone care? Either way. Is anyone alive out there? No one's alive? All right, good to see, good to see. Okay, well, since nobody has any opinions on the matter, I will just go on to 7.2. Did anybody have any questions from 7.1? Probably not. A couple of you finished the Chapter 6 test, which was good. Good to see you guys were going to finish on time and things like that. All right. Tough crowd today, tough crowd. Unit 7, Lesson 2, using elimination strategy to solve a system of linear equations. So last day we were looking at Lesson 1, Unit 7, and we're talking about solving a system of linear equations. Now, solving a system of linear equations is a really kind of scary thing, or scary sounding thing, I should say. All we're doing is you give the equations of two lines, figure out where the lines cross. That's it. That's all we're doing, trying to figure out where two lines intersect. And we can always check our answer to see if it's right by, once we get a point, we can put it into both lines for x and y and see if the left side equals the right side. And if it does, then your answer is right. So that was what we did. Now, Lesson 1 was solving graphically, which meant we take our two lines. Generally speaking, we'll put them into slope-intercept form, we'll plot them, and then look on the graph, see where they intersect. That's your answer. Perfect. Sometimes it's not quite that easy. Sometimes your lines aren't going to be nice, easy to deal with numbers. Let's say your y-intercept's like 500. Well, to draw a graph with a y-intercept of 500, it's going to, be a really big graph, and it's going to take a lot of paper, and it might not be the best method to use when solving a system of equations with, sometimes the y-intercept or some value in the line won't allow you to graph it to find out where they intersect, or the intersection point could be like 1,000 points off into the distance. So we're going to look at a different way to solve equations, system of equations, and it's called using elimination. And elimination kind of is, you want to think back to when you first learned to add and subtract, when you like lined up all the ones and the tens and then you put them over each other and you add and subtract it. That's exactly what we're going to do today. Elimination works some of the time, and we're going to learn substitution next class, and substitution works some of the time. Just depends on the system you have, and again, on a final exam or a test or whatnot, it doesn't really matter what method you choose to solve a system. Generally speaking, a question will be designed so that one method is a little bit easier than the others, but you can use whatever method you want. So if you really like graphing and you want to draw a graph and plot the lines and do that, and you think that's going to work for you, then do it. If you want to use elimination, do it. Sometimes questions will be really specific to the type of method they want you to use, and they'll say like, find the error in this method, and you'll have to look at it and be able to kind of follow along. So just be aware of that. Adding, subtracting two equations in a linear system produces equivalent linear systems. It sounds kind of complex, but it's really quite straightforward. We use this property to solve linear systems by first eliminating one variable, and we eliminate one variable by adding or subtracting. The two equations. This is called solving by elimination. All right, so solving by elimination. First example here, solve the following system by elimination. Two equations. We could plot these ones. I mean, there's nothing terribly difficult about them. We could, draw them, but it's on a graph. But it's asking to solve by elimination. So what I'm going to do is, I'm going to label my lines 1 and 2, just so I remember which one's which. It's always a good habit to get into. And this first bit might not make a whole lot of sense, but once you see it once, hopefully it just kind of makes a little bit of sense. So since the coefficients of y are equal, and we're talking about the number in front of our y term, in each of the lines, they're equal, it's the same. We can eliminate y by subtracting the equations. Then solve for the remaining variable. All right, so I'm going to rewrite my equations just down below here, and I'm going to write them on top of one another, just like they're written up above. So we're going to have 5x plus y is negative 13. It's my first equation, and 2x plus y is negative 1. So those are my two equations, and I'm going to subtract them, just like I would in grade. I don't even know what grade you add or subtract by writing things on top of each other. Probably like grade 3 or 4, I would guess, maybe 2, I don't know. Just like the old days. And what we're going to do is we're going to subtract. You can put the bottom line in brackets just to kind of remind yourself that we're subtracting everything in that second equation, not just the first term. So this might be a bit different to look at, but we're going to subtract this. We're going to go 5 minus 2x. So we're going to do the x's first. 5 minus 2x, so 5x minus 2x is going to give us 3x's. And we can only add and subtract things with like similar variables. We can't, add 5x's and y together. We have to stick with similar variables. Now the reason we're subtracting this equation is because if I go positive y minus negative y, I end up with 0 y's. And I don't even really need to write in the 0 y's because 0 times y is just 0. So I'm just going to get rid of it. But it basically eliminates that y term. That's why it's called solving by elimination. Then I do the last one here. I have negative 13, and I'm going to subtract negative 1. So negative 13 minus negative 1 is going to give me negative 12. So equals negative 12. All right, so I subtracted those two equations. I ended up with another equation, 3x equals negative 12. Now the good thing about this, 3x equals negative 12, is this is an equation, and this equation only has one variable in it. So I can solve for x. Because it is the only variable left. So I'm going to divide both sides by 3, and I'm going to end up with x is equal to negative 4. So what I just discovered was the x value where those lines intersect, the x value is -4. That's what I figured out. Now, if the x value is right, then that means my y value has to be right as well, and I can just substitute that x value into an equation to get the y value. Because if I know where it crosses the x-axis, I can put the x value into the equation, and then I can figure out what the value of y is. So determine the value of y by substituting x equals -4 in either of the original equations. So it doesn't matter which one you pick. I'm going to pick the first one just because that's the first one. So all I'm doing is bringing down the first equation, 5x plus y is -13. Now, by subtracting the two equations, I found that the x value where the lines intersect is -4, and I can put that in here. So all I'm going to do is substitute that in. So I'm going to go 5 times -4 plus y is -13. All right. Now you'll notice the only variable I have left in this equation is y. So I can find or solve for y, get y by itself. So I'm going to do some algebra here. 5 times -4 is -20 plus y is -13. And then I will add 20 to both sides to give me y is equal to 7. So from up here, I had x was equal to -4, and now I have y is equal to 7. So the solution to the system is -4, 7. Now, I know this looks like a ton of work, and there's like so many things going on, so many places to get lost, but once you kind of wrap your head around what's going on here, I hope you will find that it's kind of straightforward. I know it's maybe early, you've only seen one example. Again, when we solve a system of equations, we have two lines. They either intersect at one point, they're parallel, they don't intersect ever, or they're lying on top of each other, which means they're coincident, which means they intersect each other everywhere. The idea is, if we can figure out where the lines intersect, that's your answer. Now, it's not always going to make sense to graph them. Some people probably like doing this elimination method a bit better. But again, it just comes down to kind of preference, whichever one you want. Anybody have any questions there? Anything they're confused about? Anywhere I lost you? All right. Let's look at another example. Solve this linear system by elimination. All right, so again, we could probably graph these, but it asks for elimination. So in the previous example, the two equations we were given, the number in front, or the coefficient in front of our y term, was the same. In both examples, it was 1. So we just subtracted those two, and that eliminated the y. That's why it's called solving by elimination. Now in this example, I don't have anything that's the same. I don't have the same number in front of my x, and I don't have the same number in front of my y. So I can't just simply subtract these like I did the previous example. So no terms have equal coefficients. Look for a set of coefficients of one variable that could be made equal by multiplying one or more equations by a constant. It's just kind of a complicated way of saying, hey, could we multiply either equation by something to make the coefficients the same? So I have equations 1 and 2. No terms have equal coefficients. Look for the same one. So I'm going to decide on x here. Because my x value is 2 and 4, I could probably make those both a 4. And I'll show you what I mean by that here in a second. So I'm going to make the x terms alike. So consider the x terms, their least common multiple is 4. If I can get both my x coefficients for both equation 1 and 2, if I can make them 4, I should be okay. So what I'm going to do is I'm going to multiply equation number 1 by 2. All right, so I'm going to write down equation number 1 again. 2x plus 4y is equal to negative 4. And I'm going to take everything in that equation and multiply it by 2. All right, so I'm going to get 2 times 2 is 4x, 2 times 4 is 8y, and 2 times negative 4 is negative 8. So basically I just doubled the equation. Now if we think about graphing a line, if I wanted to just draw a quick graph of this, and you don't need to write this down, if I had 2x plus 4y is minus 4, and then 4x plus 8y is minus 8, those are the same line. What's that going to look like? 4, negative 4, it looks like something like that. Y-intercept of negative 8. It's not going to look like that at all. Probably looks something like that. This line, my 2x plus 4y minus 4, and this line, my 4x plus 8y minus 8, they're the same line. I can multiply them by 72. If I multiply each term in that line by 72, it's still the same line. If I plot it on a graph, it still looks the same. So by multiplying it, I've not changed the line at all. It's still the same line. So I've just made the equation look a little bit different by multiplying everything by 2. All right, since the coefficients of x are equal and opposite, we can eliminate x by adding the equations. Then solve for the remaining variable. All right. So what I'm going to do is I'm going to take my modified equation number 1. So equation number 1 is now 2x, nope, 4x plus 8y is equal to minus 8. So that was equation 2, or sorry, equation 1. Equation number 2 from up above, just going to bring it down, negative 4x minus 5y is equal to 5. So those are my two equations. And what I'm going to do, I'm going to write them on top of each other, and I'm going to add them together. So I'm going to add everything in the second one to everything in the first one. Why do I want to add? Well, because the signs in front of my 4 here, because the sign is positive and negative, if I add them together, I'm going to eliminate one of the variables. So 4 plus negative 4 is going to give me 0x. Now this is called solving by elimination because you're always trying to eliminate one of your variables. And if you can't eliminate one of your variables by adding or subtracting your equations, you're not solving by elimination. The idea is you need to get rid of one of the variables in order to solve the system. All right, so I have 0 x's. I don't really need to write it in, so I'm just going to get rid of it. I have positive 8 here plus negative 5. So I'm going to have negative 3y. Positive 3y. And then negative 8 plus plus 5 is going to give me 3. So I'm going to go negative 8 plus 5 is 3. Why having such a difficult time with integers here today? Negative 8 plus 5 is negative 3. Makes more sense. All right, so this is my equation. I've eliminated the x right out of the equation. Now I have 3y is equal to negative 3. I divide both sides by 3. We're going to solve for y. You end up with y is negative 1. So I've now figured out that the y value of my solution is negative 1. Now, because the solution is where the lines intersect, I can substitute that negative 1 in either equation, equation number 1 or 2, and I usually just pick whatever one's easier. But I can determine the value of x by substituting y is negative 1 in either of the original equations. So I can pick either equation. Now, I'm going to pick equation number 2 because I haven't done anything to equation number 2. It's just as good a reason as any. And I know that y is negative 1, so I'm going to substitute y is negative 1 in here. So I'm going to get negative 4x minus 5 times negative 1 is 5. Now you'll notice that the only variable I have left here is x. So we're going to solve for x to figure out what the x value is. So if negative 4x plus 5 is equal to 5, I'm going to subtract 5 from both sides. Negative, oh boy. Negative 4x. Oh, I lost my minus 5s. Let's rewrite this. Oh, there it is. Just jumped in out of nowhere. Perfect. Plus 5 is negative, and then I subtracted 5 from both sides to try to get x by itself. Okay. Negative 4x is equal to 0. I'm going to have to get x by itself. I'm going to divide both sides by negative 4. And I'm going to end up with x is equal to 0, because 0 divided by negative 4 is 0. So that is the second part of my solution. So from up above, I have the y is negative 1. From down here, I have the x is 0. So the solution to that system is 0, negative 1. That's where those two lines would intersect. Anyone have any questions there? Clarification, something I did, confused, still don't understand, want to see another example, want to go back to bed, want to study for English. All right. All rainbows. I'm with you, Leeds. All rainbows at this end too. All right, so example number 3, this is kind of the third scenario you can run into when solving by elimination. Let's look at example 1. When we did example number 1, the coefficient in front of the y terms was the same. They were both positive, so we subtracted them to eliminate the y term. That's what happened there. Then the second example, we switched things up a little bit. None of the coefficients were the same, but we said if we took every term in equation 1 and multiplied it by 2, that would double everything. And then we would have the same x coefficient. We'd have 2 times 2 is 4. We'd have 4 and negative 4. So we could eliminate the x's. Okay. In example number 3, the coefficients aren't the same. I don't have the same coefficients. So the x is a 3 and a 5. That doesn't work. That's not the same. The y is a negative 4 and a negative 6. That's not the same. So I can't add or subtract the equations directly. So what we did in the previous example is said, okay, we'll multiply everything in one of the equations by 2, and then we'll be able to add or subtract them. But that's not going to work here. If I double the first equation, I'm going to end up with 6 x's, and 6 and 5 aren't the same. And if I double the 4, it turns into an 8, and 8 and 6 aren't the same. So I can't just double something. I can't triple anything. Basically, there's no number I can multiply by either equation to make any coefficient the same. Okay, what do I do then? None of my coefficients are the same. I can't make them the same. What we have to do is we have to deal with both equations, essentially. So instead of just using one equation to double it or triple it, we're going to have to find a LCM, least common multiple, and we're going to have to make the equations the same by multiplying both of them. So just another sort of step, I suppose. So no terms have equal coefficients. Look for a set of coefficients of one variable that could be made equal by multiplying one or more equations by a constant. So if we consider the x terms, their least common multiple is 15. So least common multiple of 3 and 5 is 15. That's the smallest number both 3 and 5 will go into. To make these terms equal, multiply equation, we'll call this 1 and 2. We're going to multiply equation 1 by 5 and multiply equation 2 by 3. And then we'll add or subtract the equations like we did before. All right, I'm going to rewrite equation 1. Equation 1 was 3x minus 4y is 7. Now I said if I need to make my x term, I need to make my x term 15. So I'm going to multiply everything by 5. And then I'm going to do the same thing with equation 2 was 5x minus 6y is 8. I'm going to multiply everything in this equation by 3. And that'll make my x term 15. Once my x values are the same, or x coefficients I should say are the same, I can go ahead and add or subtract. All right, let's look at the first equation here. 3 times 5 is 15x, 5 times 4 is negative 20y, and 5 times 7 is 35. And over here, same idea, 15x, 3 and 6 is 18, and 3 and 8 is 24. So now my x coefficient for equation 1 and 2 is the same. So I'm just going to write these things on top of one another. Line up all of my x's and y's. And I'm going to have to subtract these two equations. By subtracting the equations, the x term will be eliminated because 15 minus 15 is 0. So I'm going to end up with 0x. 20 minus negative 18 is kind of like 20 plus 18, so I'm going to have negative 20 plus 18 is negative 2y. 35 minus 24 is 6 and 5 is 11. All right. I have 2y, negative 2y is 11. If I divide both sides by negative 2, I'm going to end up with y is equal to 11 over 2. I can put the negative sign on the top. So that is the y portion of my solution. So what I'm going to need to do now is substitute y is negative 11 over 2 into either equation. Doesn't matter. I can pick one, I can pick two. Might as well just pick one. So equation number 1 was 3x minus 4y is 7. And I'm going to substitute y is negative 11 over 2 in there. So I'm going to get 3x minus 4. And instead of y, oh, thank you, Cortana. So helpful. Negative 11 over 2 is 7. Now, the only thing left in my equation is x. So I can find my x value. I'm going to get 3x minus 4 times minus 11 is going to be positive 44 over 2 is 7. 3x plus 22 is 7. I'm going to subtract 22 for both sides, and 3x will be equal to negative 15. Divide both sides by 3, and x equals negative 5. So my solution is going to be my x value is negative 5, my y value was 11 over 2. There you go. So there you have an ordered pair. That's the solution to the equation. You can see that 11 over 2 would be hard to find on a graph. What's that going to be? Like 5.5. Might be tricky to find that on a graph. So maybe elimination would be the best method here. Those are kind of the three scenarios you can run into in terms of solving systems of equations. So I know the notes continue on for a while and there's a bunch of word problems. It just turns out that this unit, instead of just using substitution or elimination or graphing like we've done, they introduce some word problems to really make sure you're on your toes. So we'll look at the word problems here in a second. So just in terms of solving by solving by elimination. Does anybody have any questions about the elimination? Those are literally the three things that can happen. That's it. You can either have a coefficient that's the same, so you just add or subtract. You can have one equation that you can multiply to make the coefficients the same, or sometimes you have to find the least common multiple to make both solutions or equations the same to have those coefficients, so you can add or subtract. And it doesn't matter if you add or subtract as long as you're eliminating a variable. So if you have a negative 4 and a positive 4 in front of your x, you're going to add those together because negative 4 plus positive 4 gives you 0. If your signs are the same, like negative 4x and negative 4x, I guess I can just jot this down. You don't have to copy it down, but this might clarify some things. I'm not going to write the whole equation, but imagine if I have my two equations. I had negative 4x and 4x. If I subtract these, I have negative 4x minus 4x and negative 8x. I haven't eliminated my variable, so we don't want to do something like that. If I had negative 2y and, let's go positive 2y and positive 2y, if I add those equations together, I'm going to get 4y. So I don't want to add. What I want to do is subtract. This computer is being really special today. All right, so let's look at a few word equations, and then we'll call her a day. So I don't know how many of these I want to do. Let's maybe look at one or two of them. Using a diagram to model a situation. So it seems kind of weird that this is in this section, but we're just using a system of equations to solve an unknown or a problem. And the lines that we end up with look exactly like what we've been dealing with. So create a linear system to model this situation. The perimeter of a flag is 16 feet. The length is 2 feet longer than the width. So just reading the question, I can't just magically come up with an answer to this. I could guess and check. That'll work. For sure that'll work. It might take a while. So what I want to do is just try to draw a picture, try to understand what's going on here, and then maybe I can use a system of equations to solve this problem. So I have a flag. Sorry, I have a flag. And I have some length here, some length here, some width here, some width here. And that's kind of all I know. So systems of linear equations require two or more equations. So I need to come up with the equations. Basically, I'm given some information from the question. In the question, I'm given the perimeter. The perimeter is 16. Now, I know if I have a rectangle, if I take the length of one side, add it to the length of another side, add it to the width, add it to the width, I'm going to end up with the perimeter. And in this case, that is 16. Length plus width plus width. That's the distance around the outside. That's the definition of perimeter. Now, in order to make this equation a little bit easier to deal with, I'm going to call it 2 times L plus 2 times W is 16. So that's the first equation I'm dealing with. Equation number 2, the other piece of information I'm given in the question, it says the length is 2 feet longer than its width. So I'm going to take that and try to convert it into math. Length is than the width. All right, this is where this gets maybe a bit tricky. The length is 2 feet longer than the width. So if I took the length and I subtracted 2 from it, I would end up with the length of the width. The length is 2 feet longer than the width, or I could write it as length is width plus 2. Both those are the same. So you can see that because of the information I'm given in the question, I have a linear system of equations, 2 equations. I have 2 times the length plus 2 times the width is 16, and I have length is the width plus 2. Those are my 2 equations. All right, so sometimes it'll say create a system of equations. Basically, sometimes you'll just be interested in finding the system. And then sometimes the question will ask you to actually solve the system. So sometimes this will be a good answer. that'll be the answer that the question's looking for. It'll say create a system of equations to solve the problem, but sometimes you don't actually have to solve the problem. In the second part of the question here, it says Denise has determined the flag is 5 feet long and 3 feet wide. We need to figure out if that is a possible solution, if it's correct. So what I'm going to do is I'm going to take equation number 1, and I'm going to take equation number 2, and I'm just going to substitute the values into the equation. Basically, she's saying that the length of the flag is 5, and the width of the flag is 3. Those are L and W values. So if I have 2L plus 2W is 16, and I have length is W plus 2, I should be able to substitute these values in for length and width to figure out if they are in fact correct. She says the length is 5, so I'm going to put in a 5, and she says the width is 3. 2 times 5 is 10. 2 times 3 is 6. 10 plus 6 is 16. So that's good. You can do the same thing over here. 5 is 3 plus 2. 5 is 5. There we go. So Denise was correct. Good for you, Denise. A linear set of equations considered together from a system of linear equations let's just not worry about this for now. Let's model let's maybe look at 2 more, and then we will finish up. Using a table. Sometimes it helps to put in the information we're given in a table. So if we read the question, in Calgary, a school raised $195 by collecting 3,000 items for recycling. School received 5 cents for each pop can and 20 cents for each plastic bottle. So the idea here is we can create a linear system, represent these things. So C, we're going to let C represent the number of cans. And we're going to let B represent the number of bottles. Those are the 2 things the students collected, cans and bottles. Now, sometimes the problem with creating a table to represent these things is the table isn't always included. Imagine this wasn't here and you had to create a table to figure this question out. It might be a bit tricky doing that sort of thing, so you might just jump right to equations. But since this has a table here, we can maybe use the table to figure things out. So it says school received 5 cents for each pop can. We're going to write the refund in dollars just to make life a little bit easier. 5 cents for a can, 20 cents for a bottle. I don't have to put anything in there. Number of items. Well, I had C is the number of cans and B is the number of bottles. And I know that I have 3,000 cans and bottles. I don't know how many cans, how many bottles, but I know in total I have 3,000. The last column's kind of maybe the trickiest. If I take the number of cans and I multiply it by how much each can makes me in terms of money, I'm going to figure out how much money I got from cans. And I did the same thing with bottles. Take the number of bottles and multiply it by how much money I get per bottle. I'm going to end up with the money I got from bottles. Now it says in the question, the total money raised is $195. That's how much money I have in total. All right, so we've used a table to kind of try to organize our information a little bit here. You could likely just jump right to this step where we write down our two equations. Sometimes it helps to put information in a table. So if I look back to the question, I have the cans and the bottles. I don't know how many there are of either, but I know together there's 3,000. I know how much money I've made in total, but I don't know how much came from the cans or came from the bottles. So if I look into the third column, if I take the number, this would be equation number one, if I take the number of cans plus the number of bottles, I'm going to end up with 3,000. And then the fourth column is going to be equation number two. If I took 5 cents times the number of cans and I added it to 20 cents times the number of bottles, I would end up with $195 in total. So that is my linear system that models it up above here, 1 and 2. The second part of the question says, the school collected 2,700 pop cans and 300 bottles. Use the linear system to verify these numbers. So to verify, we substitute C and B into each equation. So just basically checking our solution. So you're going to have equation 1, C plus B is 3,000, and equation 2, 0.05 plus 0.20 is 195. I'm going to substitute C and B in. I'm going to see if I get check marks at the bottom for both, and that way I know that the solution is right. I'm not going to substitute those in and do the math, just because you guys are experts at that already. Let's look at this last system, and then we'll finish for the day. There's some extra practice questions at the bottom. You can do them, but they don't have to be done. All right, example 3. Again, we're going to try to figure out a system to solve this given the information that is given the information that is in the question. Riverboat took 2 hours to travel 24 kilometers down a river current and 3 hours to make the return trip against the current. Determine the two equations could be used to solve the speed of the boat in still water and the speed of the current. So first thing we need to do is figure out what are the unknowns, and then once we do that, we can figure out some variables that we're interested in, and then we can come up with some equations. And once we've got two equations, we can solve the equations to figure out some information. So we want to come up with a system of equations that represents the information in the question. That's kind of the point of this. Notice we're not even solving the system. We just want to come up with a system that represents things. So reading the question again, we need to figure out, what sort of variables we're dealing with. What two things don't we know? Well, we know if we go downriver, it takes 2 hours. If we go upriver, it takes 3 hours. And then we know the distance is 24 kilometers. But what don't we know? Well, we don't know how fast the boat's moving. And we don't know how fast the water's moving or the current is moving. So those are the two things we don't know in this question. If we wanted to generalize to longer trips or things like that, we'd need to know that information. So maybe we'll let B represent the speed of the boat. And I'm going to put in still water, meaning just how fast the boat goes if it wasn't in a river, if just the speed that the boat can travel. And then I'm going to use the letter C to represent the speed of the current. That's the other thing we don't know. All right, so we have a little boat. When it goes downstream, it's going to go fast. When it goes upstream, it's going to go slow. We'll just assume that the boat is always traveling at the same speed. But if you're trying to go up a river, you have to kind of fight the current sort of thing. So if I took the speed of the boat and I added the current to it, you imagine if you were standing on the shoreline, you would see a boat going past you quickly because it would have its own speed plus the speed of the current. That boat would move a little bit faster. If the boat was traveling upstream, you'd look at the boat from the shore and it would look like it was going really slow. But if you're the boat, you'd think you're going the same speed sort of idea. So this is going to be the speed of the boat with the current. Kind of seen from shore. And then B minus C is going to be the speed of the boat against the current. So if that boat is trying to fight the current. All right, we have two directions. We have the direction with the current, and we have the direction against the current. Oh boy, spelling things wrong. Oh, maybe I just don't write the word against. It's just not meant to be. All right, so the distance in both cases is 24 kilometers. If I'm going upstream or downstream, it doesn't matter. The speed I'm traveling is going to be the boat plus the current, and this is going to be the boat minus the current. The time it takes, if I am going with the current, it took 2 hours, and then against the current was 3, is that right? Riverboat took 2 hours to travel 24 and 3 hours to make the return trip. And an equation. This is the only part you wouldn't know from the question, but this is kind of one of these formulas that you just have to know. Distance is speed times time. And I think maybe it's not on your formula sheet. It's just one of those things you need to know. So the distance is, in both cases, 24 kilometers. So I'm trying to come up with two equations. Speed times the time. In the first example here, I had my speed of B plus C, and then I have B minus C. If I multiply it by the time, it took 2 hours going upstream and 3 hours going downstream. So there's my two equations. I could solve those if I wanted. I'd have to expand to distribute the 2 and the 3 through. But the question doesn't ask me to solve for anything. It asks me to create a system. I might look at Uncle Tom here, just because this is kind of a common problem that comes up a lot. And then I will call it a day. I know I said one more, but I'm going to do 2. I'm sorry. It's just this is a really, really common question. Uncle Tom invested a total of $3,000 in 2 different rates. Part of the rate was invested at 5%, and the other was invested at 7%. After a year, he earned $182. Determine equations you can use to solve for the amount he invested at each rate. So we don't know how much he invested at either rate. If Uncle Tom was a savvy investor, he probably would know these sorts of things, but he doesn't, so we're going to help him out. What information don't I know? Well, I don't know how much was invested at either rate. So why don't we come up with the amount invested at each rate. Those are the two things I don't know. So we'll call one of them X, one of them Y. You can call them A and B. You can call them whatever variables you want. So let X represent the amount at 5% and Y represent the amount at 7%. Those are the two things I don't know in the question, the 5% and the 7%. All right, so the amount invested at 5% is X. The amount invested at 7% is the Y. And I know the total amount invested was $3,000. So that's given in the question. The other thing I'm told is that I have 5% at the X, I have 7% at the Y, and in total, if I add up the interest I made, it's $182. That's the other total that I'm given in the question. I guess the tricky bit here was the amount earned is going to be the amount of money you invested at X and the amount of money you invested at Y, but I have to multiply it by the interest rate. So in this case, 5% as a decimal is 0.05, and 7% as a decimal is 0.07. So I need to come up with two equations. If I take the amount I invested at 5% plus the amount I invested at 7% and I add them together, I end up with 3,000. The other information I'm given is some of that interest is going to be at 5%, some of that interest is going to be at 7%, and in total they're going to equal $182. So that is the second piece of information in the question. So that's my system of equations. I could solve that system now by graphing. I could solve it by elimination if I wanted. And yes, once I did that, I could figure out X and Y, and then I could figure out the amount he had at each. This question doesn't ask us to actually figure out. It just asks us to determine this set of equations. So we have two equations. We can solve them. There you go. That's that. That's an hour. You guys have English exam tomorrow, so I'm not going to continue on. The learning guide looks like this. System equations, graphing. The second part is solved by elimination, which is what we just did today. And then solved by substitution is going to be next day. Now, I said that it's a really short learning guide. I said that I would probably pre-record 7.3 solving by substitution, and I will do that. So I'm going to do that this afternoon. I'll send out an email or a message in Moodle with a link. So sometime before Thursday's class, I would like you guys to look through the video. I'll make it short, like 10 minutes, 15 minutes or so. And then on Thursday's class, what we'll do is we will answer any questions you had from Unit 7 from the Learning Guide, and then I would like to look at some review material. So we'll go through a bit of an exam in class, or if you guys have any review questions, anything that you're kind of going through in terms of review on Thursday's class, you want to go through that, we can do that. So next class is on Thursday. I would like you to have watched the 7.3 before class. In class, if you have any questions about it, you can ask. And then we'll spend a little bit of time going through and finishing up Unit 7, but I want to spend the majority of the time going through a review, starting to kind of look at the exam, material that we're going to need to cover, things that are tricky, how to review. So that's where we're at. Does anybody have any questions? Okay. I'll leave you guys there. Hopefully you can get Unit 7 well underway, have it finished on Thursday, have that test, the Unit 7 test, written before the end of the week, and then you're looking at a couple days of just review next week, and we're done. That's it for this part of the course. So thanks very much, guys. Look for that recording sometime this afternoon. You can watch it tomorrow or whatnot, and then we'll start with some questions on Thursday. Have a great day, and good luck with your English studying. We'll see you guys tomorrow.